Thank you, Chairperson. I'm Fuminori Yanagimoto from the University of Tokyo. Today I will present to you about the brittle propagation in straight plates. First, I explain background. This is social background, and essentially, larger cell condenser is began to be used. So the strip plates used for hot silicon become extremely thick. So the risk of cleavage crack initiation is increasing, and the concept of double integrity is emerging. So to achieve this concept, it is needed to clarify the brittle crack propagation and arrest behavior in strip plates. However, there is no established theoretical explanation on this behavior based on the energy balance approach. On the other hand, recently the so-called local approach is being focused. And this approach, when the local tensile stress in the field of crack tip, it can satisfy the local fracture stress sigma f, the crack will propagate, and it cannot be equal to the sigma f, the crack will be arrested. Based on this concept, I proposed a numerical model to simulate the ESTO test. And based on that, Shibano evolved the model. However, these models do not use directly measured local fracture stress, and these local fracture stress has not been measured. So it needed to measure this value, but it is and by inputting the crack velocity and the crack front shape into the FBM analysis, we can obtain that. In fact, there are some researches to try measure the brittle crack local fracture stress. However, they cannot be perfect because they did not consider 3D effect. As shown in this figure shows the fracture surface after the crack arrested. There is an unbroken side ligament, and the crack front shape is cut, not straight. So this information should be taken into the FBM analysis when we implement the reproductive analysis. However, we cannot observe these formation during the brittle crack propagation. This figure is only after the crack arrested. So in order to know the crack front shape and the side ligament formation situation, we use the side group specimen. Generally, the curved crack front and the side ligament formation is caused by the stress decreasing near the plate surface. So we use the side group. It causes stress concentration near the surface, and it makes the stress, local stress along the crack front equal to one of the center of thickness. So by using this specimen, we can make the crack front as a straight one. And about the experiments, we use these steel. This is a typical ferrite pyrite steels, and this is classified by SS400 in GIS. And the specimen overview is here, and the thickness is originally 50 millimeters, and by side group the thickness is 30 millimeters. And we use the embrittlement bead to promote the cleavage crack initiation. And we make the notch by electric discharge machine in the embrittlement bead area. And this specimen is broke in brittle manner by the only remote tensile stresses. And the load is here, and the temperature in the both experiments is written in here. The temperature was kept almost constant by cooling baths, explaining the liquid nitrogen. And we have to detect the crack passing to obtain the crack velocity. We use the strain gauges to detect the crack passing. Usually, crack gauges are often used to this purpose, but crack gauge cannot be used here because the side group prevent us from using crack gauges, and there is some difference between actual crack passing and cut-off crack gauges. So, and these are experimental equipment with the 10 meganewton tensile rigs, and the specimen was connected to this rig via the tar plate and the crevice and pins. And we use these type of measurement instruments. These are high-speed oscilloscope and amplitude. And this sampling rate was 10 mega per second, and this is enough function to measure the crack velocity. And this is experimental data. We implemented 2 tests, and both fracture surface show only cleavage one, and there is no unbroken side ligament. And crack passed just under the bottom of side group, and there is no deviation from the bottom of side group. And these figures show the strain data, which the strain gauges can output to us, and this data is not filtered by anything. These are basically raw data, and strain is increasing gradually, and just after they show peak, there is a sudden drop of the value of strain. This peak means that the crack passing just beside the strain gauges. And in fact, we use 14 strain gauges for each test, but some of them cannot detect the strain transition, so we omit them from this figure. And next, we get the crack velocity. This figure shows the crack position. This is equal to the strain gauge positions, and this is crack tip time. This is the peak time. So we approximated this relationship by this equation. And by differentiating this equation, we obtain the crack velocity V. This is L differentiated by time t. So we obtain this crack velocity history for each test. Using this information, we implemented FEM analysis. In this research, we use commercial code Abacus 6.14 and implemented 3D elastic analysis. And the used model is here, and this is a quota model concerning the symmetry of Y-plane and Z-planes. And constitutive law was obtained by high-speed tensile test and low-temperature tensile test, because the steel has strongly plastic deformation. And next, to represent the crack propagation, we use this nodal force release technique. As you know, there are some methods to represent the crack propagation in FEM, for example, extended FEM. But in this research, we want to know the local stress, and we have already known the velocity and the crack path. And this method is as shown in this movie. And this method, the corrective node is released at time step, and this calculation was implemented in implicit way, and we use the ramp option. This is a FEM result. This shows the local stress normalized by the one of the center of thickness. We checked how side group worked from this figure, and dashed line shows FEM analysis in the normal plate without side group. This is the local stress started to drop at 7.5 millimeters from the center, but straight line, this is a side group specimen, about from 14 millimeters from the center, the local stress started to drop. Similar trend can be seen in both tests, so we think the side group can work. And so we average these local stress from the center to the 14 millimeters from the center. We obtained the local stress. Based on the local fracture stress criterion, this value is equal to the local fracture stress, sigma f. And the stress is nearly constant for each test along the crack length. And this figure shows only the crack length which the strain gauge can detect the crack passing. And according to these results, I will show the discussion slide. The value of local fracture stress is higher in low temperature. At the first glance, this is not corresponding with the knowledge that the crack arrestability becomes high in high temperature, but the crack arrestability dependency of temperature is due to the yield stress increasing or decreasing against the temperature. And this local fracture stress change rate is lower than one of the yield stress concerning the high strain rate. At the crack tip, there is about 10,000 per second strain rate. So this result is not incompatible with crack arrestability knowledge. And this trend, the cause is made by the charge formation we think. As you know, the cleavage plane can propagate along the 100 plane. So there is a ligament between the cleavage plane. So this ligament is broken in ductile manner and absorbs the plastic work. So the absorbed energy is become higher in low temperature because the yield stress is become higher. And this is figure shows our model calculation. The model is calculating the microscopic effective surface energy, and this is explained in yesterday's session. And by this model calculation, in low temperature, the effective surface energy becomes higher. So we think these local fracture stress trend can be explained from the theory formation. And this is the conclusion slide. The conclusion is here, but we think this data is not enough to state the temperature dependency. So it is needed to implement more and more or different types of stereo experiments. And of course, theory formation is not evaluated in quantitative methods, so it is needed to clarify the micromechanism of steel about this brittle crack propagation phenomena. Thank you for listening.